The next talk by Daniel Kondys. He works with the Czech Education and Scientific Network, established in 1996 by the network of Czech public universities. Today, Daniel will walk us through the architecture of NDK, a versatile FPGA-based network card and open source framework for high-speed network application for academia and beyond. Thank you.
This work? Yep, this is working. So, hello everyone. Thank you for the introduction. My name is Daniel Kondys. I am from Cesnet, and I'm here today to tell you about the Network Development Kit, an open source framework for network applications on FPGAs. So we're going a little bit back to the topic of that cast presented. And about the NDK framework, it's been here for a while, and it's quite large at the moment, so I could spend easily an hour talking about all the aspects of the framework. But I only have around 20 minutes, so this is more of a short briefing. And I'll be happy to answer all your questions later throughout the FDF meeting. So let's jump right into it. Let me start with some introduction and origin of the NDK framework. It is developed and maintained by Cesnet, which is NRAN of the Czech Republic, meaning it is a specialized internet service provider for national institutions, like hospitals, schools, universities, research organization, and stuff like that. It is also a research institution by itself. Also, it is part of the GÉANT association, meaning it is connected to the pan-European network, and through that also here to CERN. And on this slide, this is around as close to the current infrastructure of the Cesnet network as it gets. You can see some 100 gig lines, 200, 400 gigabit lines. And what my department is focused on is network security. That is mostly analyzing possible threats, monitoring the network, and behaving accordingly. So my specialization is in the network monitoring, where we use probes, which, well, if you take it for 100 gigabits, that's to process such high rates, data rates, it takes a lot of processing power. So for that, we use FPGA-based SmartNICs and do some offload or pre-processing of the network traffic, then for the software part to perform the analysis and detecting intrusions, stuff like that. So basically, the network monitoring is the first and foremost application Cesnet uses the NDK framework for. But over the years, there are many others. We can accelerate some other network security systems, like for intrusion detection and prevention systems, DDoS protectors. We have also developed systems for testing these network devices. There was a really nice project for realistic network traffic replay. We have also done a few low latency modules for high frequency trading applications. So that was for the introduction. Now we move a little bit deeper into the framework itself. We use, or the NDK is mainly for network applications, meaning we use FPGA-based SmartNICs. This is a very simple diagram of an FPGA SmartNIC with some USFP transceivers to connect to the network, a PCI connector to connect to the host PC, the FPGA in the middle, some external memories, and perhaps other peripherals. And what the, well, if somebody was trying to build an application on such a NIC, it would take a lot of time to manage all the different interfaces from these peripherals. So one of the key things that the NDK does or provides for the users is all of the infrastructure, all of the modules that are necessary to connect to the network, to take care of the Ethernet interfaces, as well as communication with the PC, with the server. So the key thing here is that the NDK is not just a framework where there are individual components bunched up in one repository. It's a full system, okay? So it also has its own build system that is very user-friendly. The modules and components are in VHDL, but we support both major vendors, Altera as well as AMD. We instantiate their hard IP blocks in our base components and build from that. We do some wrapping. I will get to that a little bit later. And we support the highest lines of FPGAs and the hard IP cores that the vendor provides, meaning we can reach 400 gigabits per second of processing power, or we can process this data rate in the FPGA. The NDK also provides a robust verification system. Most of it is in the UVM methodology for most of the modules and components, but we've also started using the CocoaTB framework due to its simplicity. It's written in Python, so it's much simpler than System Verilog. We also use the CocoaTB framework for simulations of for top-level simulations, but not only of the firmware, but also for the software applications and how they work together. And I have mentioned that we support the FPGAs from Altera as well as AMD, so that due to that, we are able to support wide range of FPGA cards, as well as multiple speeds and standards of Ethernet, as well as PCIe. So now let me talk a little bit more about the DMA module. The DMA helps to facilitate the communication between the FPGA and the RAM of the host PC. There are two types of DMA engines in the NDK framework. For one, there is the low latency DMA engine. As I've mentioned, some low latency modules that we have developed, this is one of them. So this is this DMA engine is it is open source and it is low latency. The trade-off is it only is able to transfer about 100 gigabits per second to and from the host PC. The other one is the DMA engine built for the high processing speed, and this one is closed source, available through our partner Dynamic, and this DMA engine is able to transfer packets back and forth at 400 gigabits per second. Of course, the latency is much worse. Talking about transferring data to and from software, I will briefly mention the software stack, which has its own repository on GitHub. It provides a Linux kernel it's called NFB. It has our own very simple NDP interface as well as the standard XDP interface. It provides a user space library with APIs in C and Python, and it also provides a DPDK driver. And on top of that, there are some applications or tools built in to help manage stuff around the FPGAs, like loading firmware to the FPGA, so reading statistics from Ethernet interfaces and stuff like that. So I have talked about how the NDK takes care of the infrastructure, and that and the user is basically left to fill this part, the application, which has interfaces to all the other parts, all the other peripherals. So, for example, to the internet, to the Ethernet or internet as well, to the host PC, external memories, and so on. The thing is, you may notice these strange names. Okay, yep, over here, MFB, MVB, and MI. These are the names of the buses that we use. There are we basically said that we need our own buses to do what we want. So for the next 3 slides, I will try to describe them as best I can in the limited time I have. But in case anybody will be interested to learn more, I will gladly tell you all about it. So first of all, the memory interface bus, the MI, is just like an AXI Lite bus or Avalon memory mapped. It's simpler, more resource efficient, but the functionality or the use cases are basically the same. For the next part, the multi-frame bus, this is probably the key part of the whole presentation, because the multi-frame bus was developed with high throughput rates in mind. So as there was a question about increasing throughput to 400 gigabits, and as a reaction to the presentation from CAST. And they said that you can't really quadruple the frequency. Well, the thing you can do is widen the bus, and for that you need to be able to transfer multiple frames or parts of frames or packets in each data word, so the data words aren't empty which would reduce throughput at the shortest packets. And this is exactly what the multi-frame bus allows. It allows you to stack frames in each data word and hence reach 400 gigabits per second at 200 megahertz frequency. And the MVB bus, the multi-value bus, is a complementary bus for the MFB. The main difference is that the values have constant width. There can be also multiple of them in each data word. Usually there's one value for each frame. So that was, now I will briefly show you an example of an application that we use for network monitoring probe. There is, well, this is an example from a 2-port FPGA card. For each network port, there is an independent pipeline consisting of parser to parse headers of the packets, to filter out unwanted traffic, RSS to distribute packets to different DMA queues, optional switching, and connection tracking. So maybe I should have mentioned that this side would be connected to the Ethernet interfaces to the network module. The other side would be connected to the DMA module and further on. And there is the configuration possible through the MI bus over here. Before we wrap up, I would like to mention other users of the NDK framework. So I've, of course, mentioned Cesnet, using it for security applications. There is Dynamic Semiconductors, who go even beyond this, and many of their applications are for data centers, like virtualization, cloud storage, machine learning, and much more. There's Magma.io, who specializes in the high-frequency trading applications. And there is also Brno University of Technology, who uses it for post-quantum encryption systems. So, to wrap up this presentation, I would, if you would take anything from this presentation, I would be happy if you took 2 points. One, that the NDK is built to support network applications at the highest throughput rates. Currently, we are at 400 gigabits. We are hoping to move even beyond that. And the second thing is that I haven't mentioned enough, that the NDK framework is, well, you basically, the most likely you wouldn't use the NDK framework is for its components, even though that is possible. But you wouldn't use it for your project. You would probably build your project on top of it. That means you would insert your application into the existing source code. And that would be all from my side. I hope I have told you something new. If you have any questions, go ahead and ask them now or later throughout the FDF meeting. I will be here until Friday. Thank you again.
Thank you very much, Daniel. So, does the audience have any questions? Now then, maybe I can ask one myself. I was interested by the collaboration that you have with the industry, in particular high-frequency trading. Like usually, under which term you collaborate? Do they participate to the development or?
Yes. So the Cesnet, it's by itself is a research or not-profit research institution. So when the Ministry of Interior of Czech Republic often gives us possibilities to work on projects with a commercial partner to build something new. So that's why we partner up with partners like Magma or Dynamic to keep them evolving. They usually do not contribute to the NDK framework itself. Sometimes they do, but usually their output is their own IP cores, and what we do is then publicly open on GitHub.
Okay, thank you very much. We have a question here.
So I see that you have a series of supported boards for your framework, but how easy would be if I just take your open source code and try to port it? If I take your code and try to port it to, let's say, a custom board that I have.
I don't know about custom boards, but other FPGA boards are frequently added to the already wide range of support in NIC. So it depends on also on the FPGA, on the manufacturer of the FPGA. So far, we only support AMD and Altera. So I'm not sure about others, but for these, it's pretty simple.
Okay. Do you have any other? We have all the way up there.
Thank you very much for your presentation. It was great. Do you have any experience with the Altera Hyperflex silicon architecture regarding timing closure in your design? Because it's a very high-speed design. Do you have any experiences in that area?
Yes, of course. The thing is that, well, 200 megahertz is mostly the frequency that we work with, and it's not that hard to close the timing for our applications. But we usually don't have to do some very precise maneuvering with the architecture of the FPGA, with the Hyperflex architecture. We're talking about basically the synthesis tools can handle it by themselves. So I personally don't have any experience with really going deep and constraining it to use these Hyperflex registers.
Anyone else? If not, then we can thank Daniel again.